Deterrence AI, the leading blog in proactive security.
It's mind-blowing to think that by next year, we're looking at a world with billions of devices all talking to each other thanks to the Internet of Things.
It really is.
Everything, I mean everything, from our thermostats at home to those massive pieces of industrial equipment in factories, all constantly exchanging data.
Yeah, and the real unsung hero making so much of this large-scale connectivity even possible. That's the low-power wide-area networks, or LPWANs as they're often called.
LPWANs, right. It's the key to enabling this huge interconnected world without every single device needing to be plugged into a power outlet.
Absolutely. And imagine if they all needed a hefty data plan like our smartphones.
Yeah, the cost would be astronomical.
Think about trying to manage thousands of sensors spread across a massive farm if each one needed a power cord or burned through batteries every couple of days.
It would be a logistical nightmare.
LPWANs have been specifically designed for these scenarios: long distances, tiny sips of power, perfect for those devices that just need to send small bits of information every now and then.
Like a moisture reading from a field, or whether a parking space is available.
Exactly.
So we've got this massive explosion in the number of connected devices, and LPWANs are this foundational technology, making it all feasible. But if you're trying to connect your own devices, you quickly realize there isn't just one way to do it.
There are actually quite a few competing technologies out there.
Right, and that's where this deep dive comes in. You sent over a fantastic guide comparing the main LPWAN contenders, and I'm keen to dig into this.
I'm happy to help break it down.
Awesome. So our mission today is to cut through all the technical jargon and really understand the core differences between LoRaWAN, NB-IoT, and Sigfox. For someone who needs to connect their devices, it's a bit of a jungle out there.
It can be. So consider this your map to navigating that jungle. We're going to look at each technology in detail, how it's actually built, the technical architecture, how they perform in real-world deployments, the nuts and bolts of actually getting them set up, the security features they offer, and of course the costs involved.
And importantly, we'll also highlight the specific types of applications where each one truly shines.
Exactly. What are the sweet spots for each technology?
And because our listeners are primarily based in Australia, we're also going to look at how these technologies fit into the Australian landscape.
Of course, things like spectrum regulations and which telecommunications companies are offering these services here.
Perfect. So let's jump right in, starting with LoRaWAN. This seems to be a really versatile option, am I right?
It is. LoRaWAN stands for Long Range Wide Area Network. It's a leading open standard LPWAN protocol developed and maintained by the LoRa Alliance.
The LoRa Alliance, okay.
And that open standard part is really key here. The technical specifications are publicly available, so anyone can build devices or even set up networks based on LoRaWAN. You're not locked into a single company's proprietary technology.
Okay, so it's not a walled garden controlled by one company. That sounds like it could lead to more innovation and hopefully lower costs over time. And the guide you sent mentions that it operates in these unlicensed ISM bands. There were examples like 868 megahertz in Europe, 915 megahertz here in North America and Australia, and 433 megahertz in Asia. So for the average user, what does it actually mean when a spectrum is unlicensed?
Think of it like a public park, but for radio waves.
Okay, a public park.
You don't need to obtain a specific license or pay any fees to use these particular frequencies.
So that lowers the barrier to entry, especially for smaller companies or startups.
Exactly. It can significantly reduce the initial cost of deploying a network. However, just like a public park, you have to be mindful of others. There's always the potential for interference because anyone can use these frequencies.
Right, so it's a shared resource, kind of like a free-for-all on the airways.
In a way, yes. It could be another IoT network operating nearby, or even some industrial equipment that happens to emit signals in the same band. But fortunately, LoRa incorporates clever techniques to mitigate interference, which we'll get to in a bit.
Got it. Lower cost to get started, but you have to be a good neighbor and play nice with others on those frequencies?
Precisely.
Now, the guide also mentions the star of stars topology.
Ah, yes.
That sounds like something straight out of a science fiction movie.
It does, but it's a fairly straightforward concept, really. It describes how the different parts of the network communicate with each other.
Okay, break it down for me.
Imagine you have your sensors or actuators out in the field. These are the end devices with LoRaWAN modules inside. They transmit their data wirelessly, and any gateway within range can pick up those signals.
The gateways are like listening posts, strategically placed to pick up these messages.
Exactly. Think of them as relay stations. They receive those radio signals from the end devices and then forward that information to a central network server, usually using a standard internet connection.
Okay, so the sensors, the little guys, are broadcasting their messages, and there are multiple gateways, the listeners, that could potentially pick them up.
Yes. And because there can be multiple gateways receiving the same message, the network server needs to be smart about handling that.
Right, so it needs to figure out which one to use and get rid of the duplicates.
Exactly. And that's just one of the things the network server does. It also manages security, optimizes data transmission rates for each device using something called adaptive data rate, or ADR, and then routes the actual data to the right application server, where it can be used by whatever software service is collecting that information.
And there was also mention of a join server. Something about secure over-the-air activation, OTAA.
Right.
That sounds like it's responsible for securely onboarding a new device when it first joins the network.
You got it. When a new LoRaWAN device wants to connect for the first time, it goes through this OTA process, which is managed by the join server.
Like a digital handshake?
Exactly. The join server securely stores the initial secret keys for all the devices and generates the unique session keys that they will then use for encrypting their communication once they're on the network.
So this join server is separate for a reason.
It is. It's a security measure. By keeping that initial key management separate, you prevent the main network server from ever having access to those root keys. So even if the network server were to be compromised, those master keys remain safe.
Ah, that's a clever way to add an extra layer of protection.
It is.
So just to recap, devices talk to gateways. Gateways feed the network server, which then routes the data to the appropriate application server, and the join server manages that initial secure handshake.
Perfect summary.
Awesome.
Yeah.
Now let's get a bit more technical and talk about the actual radio technology behind LoRaWAN, the LoRa physical layer, as it's called. It's based on this chirp spread spectrum, or CSS, developed by a company called Semtech. I remember reading that this technology is particularly good for achieving long range and dealing with interference. Is that right?
Yes, it is. Chirp spread spectrum is a really clever way to transmit radio signals. It encodes the data by sweeping the signal's frequency up and down over time.
Kind of like a siren changing pitch.
Yes, a good analogy. These frequency sweeps create these chirps, and this spread spectrum approach makes the signal more robust, it can travel further, and it's less affected by interference from other signals operating on a single specific frequency.
So it can punch through the noise, so to speak.
Precisely. And a key element of how this works is the use of spreading factors in LoRa. They're numbered from SF7 to SF12.
Spreading factors.
Think of these as different gears for your radio.
Okay, gears.
A lower spreading factor is like a high gear. You get a faster data rate but a shorter range, and you're more susceptible to interference.
Okay, so speed, but less resilience.
Yeah. A higher spreading factor is like a low gear. You get a much longer range and much better immunity to noise, but you have to sacrifice data speed.
So it's that classic trade-off, speed versus distance and reliability, like choosing between sprinting and going for a long hike.
A perfect analogy.
And I seem to recall that LoRaWAN has a clever way of managing this trade-off, right? Something called adaptive data rate.
You're absolutely right. Adaptive data rate, or ADR, is a key part of LoRaWAN. The network server, that central brain we talked about, constantly monitors the signal quality from every device on the network. If a device has a strong, clear connection to a nearby gateway.
So if it's practically next door to a listening post.
Yeah, in that case, the network server can tell the device to use a lower spreading factor, so higher speed, and maybe even reduce its transmission power to save battery.
So the network is smart enough to say, hey, you're close by, you don't need to shout, just whisper.
Exactly. And what's really clever is that this not only makes the network more efficient by freeing up airtime.
Less chatter on the radio waves.
Right. But it also saves precious battery life on that device. And on the flip side, if a device is further away or experiencing a weaker signal, maybe there are some obstacles in the way.
Out in the countryside or inside a building.
Yeah, in those situations, the server can instruct the device to use a higher spreading factor, so slower data rate, but more reliable communication over that longer distance.
So it's dynamically adjusting based on the conditions.
Precisely. ADR is all about the network intelligently managing its resources, ensuring each device only uses the bare minimum power and bandwidth it needs to get the job done. That's super crucial when you have thousands or even millions of devices out there.
Makes a lot of sense. Now, the guide you sent also mentioned something about device classes, Class A, Class B and Class C. What's the key difference between these?
These classes dictate how a device handles messages sent back to it by the network.
Okay, so downlink communication.
Exactly. Class A is the most energy efficient. A Class A device only listens for incoming messages in 2 short windows right after it has sent its own message.
So it basically sends its data and then opens up a quick window to see if anyone has a reply.
Exactly. And if there's no message waiting, it goes right back to sleep.
Got it. So very energy efficient because it's only listening for a tiny fraction of the time.
Yes. Which makes Class A ideal for battery-powered sensors that only need to send data occasionally, like a temperature reading or a simple alert. They don't need to receive commands very often.
Okay, so it's a mostly one-way conversation with short bursts of listening. What about Class B?
Class B devices can receive more downlink messages but use a bit more power. In addition to those short receive windows after sending an uplink message, Class B devices open additional receive windows at scheduled times. These times are synchronized across the entire network using beacon signals from the gateways.
So they have these extra listening times that are coordinated across the network.
Yes. This lets the network send downlink messages with a bit lower latency than Class A because you don't have to wait for the device to wake up and send an uplink message first.
So it's a bit more responsive, but it comes at the cost of some extra power consumption.
Right.
And then there's Class C, which I imagine is the most responsive but uses the most power.
That's the gist of it. A Class C device essentially keeps its receive window open almost all the time, only closing it briefly when it needs to transmit its own message.
So it's always listening and ready to receive a message.
Pretty much. This means you get the lowest possible latency for downlink communication. But keeping the receiver active all the time does consume a lot of power.
Right, so not ideal for battery-powered devices.
Not really. Class C is more suitable for devices that have a constant power source or in situations where very fast response times are absolutely critical, like in some industrial control systems, where even a small delay could be problematic.
So there's this clear trade-off, power saving versus how quickly you can get a message back to the device. It's great that LoRaWAN offers these different options to suit different needs.
It makes it very flexible.
Now, switching gears a bit, let's talk about security. This is obviously a huge concern with any network of connected devices, especially as we're moving towards a world with billions of these things out there. What kinds of security features does LoRaWAN incorporate?
LoRaWAN has actually been designed with security in mind from the very beginning.
Okay, so it's not an afterthought.
Definitely not. Every single device has a unique set of identifiers. During that initial over-the-air activation process, the device and the network go through this mutual authentication dance using pre-shared secret keys.
So both sides are verifying each other.
Right. And once a device joins the network, all communication is protected using AES-128 encryption.
AES-128 encryption. For people who aren't tech-savvy, is that a strong encryption standard?
It's a very robust and widely used encryption standard. It's the same level of encryption used for things like online banking. And there are actually 2 separate layers of encryption in LoRaWAN. One at the network level, which protects the integrity of the messages and ensures they haven't been tampered with, and another layer that encrypts the actual application data, the content of the messages, all the way from the device to the application server.
So even if someone were to intercept the data, they wouldn't be able to read it without the keys.
Exactly. And what's even more reassuring is that the network server, which is responsible for routing those messages, doesn't actually have access to the application data's encryption key. So even the network server itself can't snoop on the content of the messages.
Okay, that's a really important point for anyone concerned about privacy and keeping their data secure.
It is.
So we've covered the technology itself, but let's get practical for a moment. How do you actually go about deploying a LoRaWAN network?
That's one of the great things about LoRa, and because it's an open standard, you have several different options.
Options are always good.
Right. One option is to build a completely private network.
So you own and control the entire infrastructure.
Exactly. You buy the gateways, you set up your own network server, and you have complete control over everything. This is often ideal for large industrial facilities, university campuses, or agricultural operations where they need a high degree of control over their data and coverage.
Okay, so if you have the resources and expertise, you can go fully DIY. What are the other options?
Then you have public networks, where you basically subscribe to a service provided by a telecommunications company or a specialized IoT service provider.
Kind of like signing up for a mobile phone plan, but for your devices.
That's a good way to think about it. And in this model, the service provider takes care of building and maintaining the entire network infrastructure. You just pay a monthly fee and get access to their network.
So less upfront investment, but you're relying on that external provider.
Correct. And then you have community networks, which are often volunteer-driven initiatives where people collaboratively deploy gateways and share network access.
Kind of like a crowdsourced network.
Exactly. The Things Network is a great example of a global community network for LoRaWAN. These community networks are often free to use for non-commercial purposes, which is a fantastic way for hobbyists and small-scale projects to experiment with LoRaWAN and get started without a big financial commitment.
So a good way to dip your toes in the water before you dive in head first. That's a really nice range of deployment models to choose from. It gives you a lot of flexibility depending on your needs, resources, and risk appetite. Finally, let's talk about the ecosystem surrounding LoRaWAN. Is there a strong community and support network behind this technology?
Absolutely. The LoRa Alliance has done a fantastic job of fostering a really vibrant ecosystem around LoRaWAN. There are companies that manufacture the chips, companies that design and build the modules, companies that make all sorts of end devices, gateway providers, network server software developers, and a huge community of application developers.
So it's not just a technology in a vacuum. There's a whole network of companies and individuals working with it and building upon it.
Precisely. And this active ecosystem helps to drive down costs, encourage innovation, and ensure that LoRaWAN remains a relevant and future-proof technology.
That's great to hear. It sounds like LoRaWAN has a lot going for it.
Yeah.
All right, let's move on to another major player in the LPWAN space, NB-IoT, which stands for Narrowband IoT. This one takes a fundamentally different approach by operating within the licensed cellular spectrum. Right.
You're absolutely right. Unlike LoRaWAN, which operates in those shared unlicensed bands, NB-IoT is a cellular technology. It has been standardized by 3GPP, the same organization that develops all the major cellular communication standards like 4G and 5G.
So it's riding on the coattails of the massive cellular infrastructure that's already in place around the world.
Precisely.
And I understand that NB-IoT actually leverages a lot of the existing cellular infrastructure.
It does. Instead of deploying entirely new networks, NB-IoT operates within the licensed spectrum bands that have already been allocated to mobile network operators.
So the big telcos.
Exactly. Think of it as piggybacking on the existing cellular network infrastructure.
So for the end user, this means that you don't need to set up your own network or worry about interference in unlicensed bands. You're essentially partnering with these big telecommunications companies. How does the network architecture actually work for NB-IoT?
It's designed to be tightly integrated with the existing cellular network. You have end devices, your sensors or actuators that are equipped with special NB-IoT modems.
And these modems need a SIM card, just like our mobile phones.
Yes, just like a mobile phone. These devices communicate with the existing cellular base stations, the ones you see on towers everywhere.
So the same infrastructure that our phone calls and mobile data go through.
Precisely. The existing base stations have been upgraded with software to support NB-IoT communication using a very narrow slice of their allocated spectrum.
Okay, so they're carving out a little piece of their bandwidth for NB-IoT.
Yes. And the data from those NB-IoT devices then travels through the mobile network operator's core network.
That's all the behind-the-scenes infrastructure that handles things like routing and billing and so on.
Precisely. It takes care of all the heavy lifting, authenticating the device, securely routing the data, and connecting to the various application servers where that information is ultimately used.
And I recall the guide you sent emphasized that it being a 3GPP standard is a really big deal. What are some of the advantages that come with that?
It brings a lot of benefits to the table. First of all, 3GPP standardization means you get interoperability. Devices and network equipment from different vendors should all work together without any major compatibility issues.
So no headaches trying to get things to talk to each other.
Exactly. It also opens up the possibility of global roaming. So in theory, your NB-IoT device could connect to compatible networks in other countries, just like our mobile phones can.
That would be a huge advantage for applications like asset tracking or supply chain management where things are moving across borders.
Absolutely. And perhaps most importantly, it leverages all the research, development, and especially the stringent security measures that have been baked into cellular networks over decades.
Right. Cellular networks are generally considered very secure.
They are. And by being part of that framework, NB-IoT gets to benefit from all that inherent security and reliability.
That sounds like a huge plus for anyone concerned about the security of their data, which, let's be honest, is everyone these days.
It's definitely a key consideration. And the fact that NB-IoT is part of that 5G roadmap, the next generation of cellular technology, means it's likely to be supported and continuously improved for many years to come.
So it's a future-proof choice as well. Now, you mentioned that there are actually 3 different ways NB-IoT can be deployed within the existing LTE spectrum.
Yes. In-band, guard-band, and standalone.
Could you briefly explain what those different modes actually mean?
Sure. These are basically different strategies that mobile network operators can use to squeeze in the necessary frequencies for NB-IoT within their existing 4G bands.
Okay, so they're making room for NB-IoT alongside the regular LTE traffic.
Precisely. The most common approach is in-band deployment. This uses a dedicated chunk of resources within a standard 4G carrier. Think of it as allocating a lane on the highway for NB-IoT traffic.
Okay, so a dedicated lane for the low-power devices.
Right. Then there's guard-band deployment. This takes advantage of those tiny slices of unused spectrum that exist between adjacent LTE carriers, kind of like using the shoulder of the highway.
Making use of every bit of space. What about the standalone mode?
Standalone deployment means using a separate frequency band altogether, often repurposing frequencies that were previously used for older 2G or 3G technologies. It's like building a separate road specifically for NB-IoT.
I see. So different options for the telcos depending on their specific situation.
Exactly. It gives them flexibility in how they roll out NB-IoT.
Now, just like with LoRaWAN, power consumption is a major concern for a lot of IoT applications. What mechanisms does NB-IoT use to save battery life on these devices?
NB-IoT has 2 main power-saving modes. The first one is called power-saving mode, or PSM. When a device goes into PSM, it essentially takes a very long nap.
Okay, a digital hibernation.
Yes, it enters a deep sleep state and becomes unreachable for extended periods.
So it's completely offline, so to speak.
Yes, but it's still registered with the network, so when it wakes up, it doesn't have to go through the whole process of reconnecting. It just wakes up, checks for any messages, and then goes back to sleep. This can significantly extend battery life.
But the downside is that if you need to send a message to the device, you have to wait for it to wake up on its own schedule.
Exactly. That's the trade-off. You get amazing battery life, but higher latency for any downlink communication.
And what's the second power-saving mode?
That's called Extended Discontinuous Reception, or EDRX. This mode is less extreme than PSM. The device basically extends the intervals between checking for incoming messages.
So instead of checking every few seconds, it might check every few minutes or even hours.
Yes. This strikes a better balance between reachability and power consumption. You get lower latency than PSM, but not as long a battery life.
So different tools for different scenarios, depending on how responsive the device needs to be versus how long you need it to last on battery power. Now, switching gears to data rates, I recall that NB-IoT can generally handle much higher speeds compared to both LoRaWAN and Sigfox.
Oh, yes. It can handle significantly higher data rates. While the actual speed you get in a real-world deployment can vary, NB-IoT is capable of reaching peak data rates of hundreds of kilobits per second, especially with the newer versions of the standard.
That's considerably faster than the other 2 technologies we've discussed.
It is. And NB-IoT also supports full 2-way communication, so data can be sent both to and from the device, and it has lower latency compared to, say, LoRaWAN Class A or B. And it can handle both IP-based data, which is the language of the internet, and non-IP data as well.
So it opens up possibilities for applications that require more data or faster response time.
Precisely.
Now let's talk about security. You mentioned earlier that NB-IoT inherits a lot of the security features of traditional cellular networks. What does that look like in practice?
NB-IoT leverages the decades of experience and research that have gone into making cellular networks secure. First of all, it uses SIM-based authentication, which means the identity of the device is verified using a secure chip embedded in the SIM card.
So it's hardware-based security, not just relying on software.
Yes. And the communication between the device and the base station is encrypted using well-established and robust cellular security algorithms. On top of that, you have all the security measures that the mobile network operator implements within their core network.
So multiple layers of protection.
Exactly.
Now, for someone who wants to actually deploy NB-IoT, does that mean they have to work directly with a mobile network operator?
That's right. Unlike LoRaWAN, where you have the option of setting up your own private network, with NB-IoT, you're reliant on the mobile network operators.
Yeah, so companies like Telstra, Optus, and Vodafone here in Australia.
Exactly. You're basically subscribing to their service and using their infrastructure.
Okay, so it's a partnership with the big telcos. And what about the ecosystem of devices and modules for NB-IoT? How does it compare to something like LoRaWAN?
It's a bit younger than the LoRaWAN ecosystem. LoRaWAN has been around for a bit longer and has a very diverse and active open source community. NB-IoT is catching up quickly, though. It's benefiting from the massive scale and the research and development muscle of those big cellular technology companies that are making NB-IoT chips and modules.
So even if there aren't quite as many smaller players, you're leveraging the expertise and resources of these industry giants.
Precisely.
Okay, that gives us a really good understanding of NB-IoT. Now let's move on to our third LPWAN contender, Sigfox. This one uses a really interesting approach with its ultra-narrowband technology.
It does. Sigfox has always been a bit of a unique player in the LPWAN landscape. Historically, they operated as both a technology provider and a network operator.
So they wore two hats.
Exactly. They built out their global network through partnerships with local Sigfox network operators, or SNOs.
And their technology relies on this ultra-narrowband modulation, which also operates in those unlicensed ISM bands like LoRaWAN.
That's right, although they typically use different frequency ranges depending on the region.
Now, as we mentioned at the beginning, the Sigfox company was acquired by Unibiz back in 2022. What does this mean for someone looking at Sigfox today?
That's a crucial point to consider. The acquisition means that the long-term plans for the technology and the network are now in the hands of Unibiz.
So there's a new captain steering the ship.
Exactly. And because of this change, it's absolutely essential to verify the current operational status, coverage, and support commitments in any region where you're considering using Sigfox.
So a bit of a buyer beware situation.
In a way, yes, the situation could vary significantly from one country to another.
Okay, good to know. So putting that aside for a moment, let's dive into the actual architecture of a Sigfox network. I understand it's considered to be quite simple and centralized.
It is. Sigfox devices are incredibly simple by design. They transmit very short messages using this ultra-narrowband technology, and they don't need to do any complex synchronization with the network.
Okay, so they're designed for minimal complexity.
Exactly. And because of that, they aim to be very low cost as well.
That's always attractive. What about the base stations?
The base stations in a Sigfox network are essentially very sensitive radio receivers. They're constantly listening for those faint UNB signals across a wide frequency band. They don't handle any complex connection management or scheduling. They just receive those messages, add a timestamp, and securely forward them to the central Sigfox cloud.
So they're like ears that are always listening for those tiny whispers from the devices.
A great analogy. And because those signals are so weak, a single message might actually be picked up by multiple base stations, which is a good thing.
Right. It improves reliability.
Exactly. It increases the chances that the message gets through.
So all the intelligence really resides in the cloud then?
Precisely. The Sigfox cloud is where everything happens. Processing the data, eliminating duplicates, authenticating devices, applying network rules, and then making that data available to applications through APIs. It even manages the very limited downlink communication that's possible with Sigfox.
So the base stations are the ears, and the cloud is the brain.
A great way to summarize it.
Now, let's talk a bit more about this ultra-narrowband technology. You mentioned it involves a trade-off, very low data rates in exchange for long range and high sensitivity.
Exactly. By using an extremely narrow slice of the spectrum for each transmission, Sigfox can achieve remarkably low power consumption and send signals over very long distances.
So it's sacrificing speed for distance and longevity.
Exactly. And the narrow bandwidth also means the receivers can be incredibly sensitive, picking up even the faintest signals.
Which is essential when you're dealing with those tiny battery-powered devices that can only transmit weak signals.
It's crucial. But the downside, of course, is that you're limited in how much data you can actually send. Sigfox data rates are very low.
How low are we talking?
We're talking about raw data rates in the range of 100 to 600 bits per second.
That's really slow compared to what we discussed with LoRaWAN and NB-IoT.
It is. The Sigfox protocol was intentionally designed to only handle tiny messages. The maximum payload size is just 12 bytes.
12 bytes.
And there are limits on how many messages a device can send per day, usually around 140 in most regions.
So definitely not suitable for streaming video or anything like that.
Not at all. Sigfox is all about sending small, infrequent messages, like a sensor reading or a simple notification.
Then what about sending messages back down to the device? I understand that downlink communication is very limited with Sigfox.
Yes. Devices can essentially request a short downlink message immediately after they've sent an uplink message.
So a quick acknowledgement or a simple command.
Exactly. But the maximum size of that downlink message is just 8 bytes. And there are limits on how many of these downlink messages a device can receive each day.
So Sigfox is very much a one-way street, optimized for sending small bits of data from the device to the network.
You could say that, yes. It's not really designed for applications where you need frequent two-way communication.
Okay, now let's talk power consumption. Sigfox is often touted as being incredibly energy efficient, right?
It is. That's one of its major selling points. The combination of the ultra-narrowband modulation, the very simple communication protocol, and the fact that it's mainly focused on sending data rather than receiving it.
So it spends most of its time asleep.
Exactly. All of this contributes to extremely low power consumption. Devices that only need to send a few tiny messages per day could potentially operate for a decade or more on a single battery.
That's really impressive. That kind of longevity would be a game changer for applications where replacing batteries is difficult or expensive.
It's ideal for those deploy and forget scenarios.
Now, you mentioned earlier that Sigfox traditionally relied on a public network model.